So, in this following lecture, we will consider the entanglement entropy in conformal field theory. One plus one dimensional conformal field theory, and this is a case where calculation can be done pretty easily and give a lot of information on what is going on. And in particular, what I will do right now will be a crucial point, so please ask me questions. And so, what we would like to know, we have this one-dimensional line between 2 points U and V. Let's call this plane W. And we would like to calculate the entanglement entropy of this segment with respect to the rest of the system. And in the plane W, this corresponds to this n-sheet Riemann surface, where there is a branch cut here, where I remind you that I explained 2 hours before. That means that if I turn around this point, by turning around this point, I don't end up just here, but I end up in the second sheet of the Riemann surface. Then I turn many other times, and time until I come back to the original plane. Okay, this is the geometry in which we would like to work, and in conformal field theory, calculations are easier because we can use conformal mapping, that's why I call conformal field theory, in order to obtain this object. Let us so first sketch how we can take this n-sheeted Riemann surface and see how we can map to a surface where we know everything, that is the complex plane. As a first step, we take this n-sheeted Riemann surface and we apply Mobius transformation is called, or bilinear, I don't know how you know it, that is a W minus U divided W minus V. That what does take the real axis into the real axis. As you see, if W is real, also the zeta is real, and map the point U into 0. Okay? 0 is equal to zeta of U, and the point W into infinity, let's say minus infinity, equal to zeta of V. So the branch cut before was between U and V, now ended up between minus infinity and 0. And this is a very standard geometry. What I'm saying is that you have to cut n time around the origin in order to get back to the original plane. This surface can be easily uniformized to the complex plane. Let's go here and by the transformation z equals zeta to the power 1 over n, that take this surface and just map into the complex plane where there is nothing. Okay. And you see that each of the original sheet of the Riemann surface is in a wedge defined by the angle q pi over n. Okay, so each of these sheets end up in a wedge of q pi over n. There are n of them, and they fill all the complex. So this is the transformation that uniformizes our n-sheet Riemann surface to the standard complex plane. How we can use this? We can use to calculate the expectation value of the stress energy tensor in this plane, in this n-sheet Riemann surface. And to do so, we use the transformation property of the stress energy tensor, that is the following: Tw equals prime square z plus c over 12 Vw. Okay, where, let me say before what are the values t, this object is called Schwarzian derivative. It is just z prime third derivative of z minus 3 alpha, if I remember correctly, yes. Ah, no. Sorry, I'm using the other notation. V second square divided by square. Okay? So it's just a combination of first, second, and third derivative of W. And I remember W is the composition of these three objects, and W equals, no, it's the other way around, Z equals W minus U divided W minus V. U1 over A. Okay, so it's the opposite transformation of the exactly same focus on that. Okay, so this formula derived by Beller-Nicolai etimology of the 84 tell us how the stress energy tensor change under a conformal map. I don't know whether you know this formula. Okay, proving it will be quite long, but all you need to know is that, okay, if I make a conformal mapping of a given conformal field theory, the stress energy tensor change under conformal transformation in this way, given by this formula. Okay? And now we want to use this formula for our problem. That means I can take the expectation value on both sides of this expression. If I take the expectation value on both sides of the expression, what I get is that the expectation value of PW in the L-shaped ring surface is equal to something proportional to the expectation value of the stress energy tensor in complex plane. But this is clearly zero. So expectation value of Tz on the complex plane is 0. Why is 0? Because by translational invariant should be a constant. Okay, so surely it should be a constant. And the integral of this constant should be also finite, and the only number that makes this is 0. Okay, so Tz is 0. The only thing that is left is this Schwarzian derivative. Now we can plug in this expression into this one, make the free derivative. I leave you as exercise. It's quite. You just make first, second, and third derivative, and then you make this particular combination, and you get clearly something proportional to C, because it's the only thing left here. And it's C over 284, 1 minus 1 over n squared, U minus V squared by W minus U, W minus V. I hope I can put all the square at the right place. Yes. Okay. So the expectation value of the stress energy tensor in this Riemann surface is given by this expression just by using how it transforms under conformal classification. And this is something that we can make only for conformal field theory, and this is the reason why in conformal field theory all these calculations are easy. Now, by the definition of twist field, what is this object? If you take just the last line of the last lecture, what we find is that this is tau n u, tau theta n v, t w divided by tau n u, tau n theta v, evaluated on the complex plane. Okay? You remember that tau a twist field that allow us to change expectation value on the end sheet of the Riemann surface into expectation value on the complex plane by proper insertion of that. And Tj is the stress tensor of the field one that we call phi j. There are n of them, they are all the same, so this is one of them. In particular, the total stress energy tensor of all the theory is just equal to sum over j that goes from 1 to n of this Tj. So if I write the corresponding expression for the total stress energy tensor, not for one of a single field, what I get is that tau nu, tau tilde v, t w on the complex plane divided by tau n u, tau tilde n v on the complex plane is equal to this c over 12, 24, sorry. I multiply the previous expression by n because these are all the same. All the Tj is the same. Let me write just down here. C over 24, n minus 1 over n, w u minus v squared, w minus u squared, w minus v squared. And this formula actually ends up our calculation. Why? Because probably for the people that are familiar with conformal field theory, this formula should remind you something. That is the so-called conformal mode identities that relates the expectation value of primary field with the expectation value of the same primary field with the stress energy tensor. Okay? I just write this formula and you will see the similarity for the people that don't know it. So if I have some primary field, the expectation value of the stress energy tensor times primary field in Z1 bar Z2 bar divided by, always on the complex plane, 5 is equal to delta, the scaling dimension of the field, let's call delta 5, Z1 minus Z2 squared divided by Z minus Z1 squared, Z minus Z2 squared. This is exactly the same formula, as you can see. Just that where in this formula is appearing a primary field, okay? In this formula, instead you get this twist field. What does the equality between these two formulas tell us? Okay? The insertion of a stress energy tensor into a correlation function is related to the change of this correlation function under a conformal transformation. Okay? So if these two formulas are the same as they are, this tells us that the twist field transform under conformal transformation exactly like primary field, where instead of the scaling dimension, you have this number. Okay, so twist field transform under conformal transformation like primary operators of, let's say, fake scaling dimension delta tau n equals delta tau n tilde equals c over 24 n minus 1 over f. First of all, I call this object fake scaling dimension because, again, for the expert in conformal field theory, you know that a given conformal field theory has a certain operator content and only that. Like there is the Ising conformal field theory that has operator of dimension 0, 1 over 16, and 1/2. These are the only numbers. There cannot be other numbers like this one. So this object just transform like primary field, but are not primary field of the theory. Okay? But the fact that they transforms like primary field basically ends up the calculation. Because we know that I primary field 5 Z1, 5 Z2 on complex plane as correlation function that okay, like Z1 minus Z2 to the 4 delta phi. I'm assuming that as it's the case here, that operator and this homomorphic and anti-homomorphic part of the operator have the same scaling dimension as it comes from here. Okay, but so if you have this for primary field, even the two-point function of our primary field will have exactly the same expression, just where I should replace this 4 delta phi with 4 times this guy here. This allows me to conclude that tau nu, tau tilde nv, that is exactly the trace of rho a to the n that I was searching for, apart some normalization that I cannot fix, is equal to Cn, this normalization that I cannot fix arbitrarily. Let's put some lattice cutoff, C over 6, n minus 1 over n. Okay, so I use exactly this expression.
So it's not obvious why you can use that. I mean, from there, just the point that you have something like primary. This transforms under conformal transformation like a primary field. The property of transformation under conformal transformation completely determines everything. You have. That's primary field. Why it's then fake? I mean, why it's not primary? Then your tau's just primary field of the theory.
It's not a primary field of the theory because the primary field of the theory are classified in a finite number, and they are not here. N can be any number, any integer number for what we have done, and this, like in the Ising field theory, for any portrait that does not exist a field with this dimension, a primary field. And the difference, in fact, of this is exactly in these constants that are arbitrary. And usually, when you consider the primary field, you say, I have an arbitrary constant here. But by normalization of the fields, that are the only independent things of the theory, I can fix this object to be 1. Okay? Here, instead, I already normalize all the theory by fixing the primary field. That's the one that really define the theory. So there is no normalization around that I can play with. And it's left some arbitrary constant that I divided in 2 parts just for being more clear, a dimensional part that I put with U minus V that is given by the ultraviolet cutoff, and then dimensionless part that is the Cn. This is just arbitrary. I would have called everything Cn and would have been fine. It's just for dividing what has dimension from what does not have dimension. And this is the only difference, in fact, between a real primary field and a fake primary field. That being not an object that defines the theory, I cannot fix its normalization arbitrarily. Its normalization of tau is fixed by the normalization of this. That's why calculating this Cn is basically impossible. Okay? But what we are really interested in is this part here. Okay? Because this object has been calculated now for integer n. I was saying that in order to calculate the entanglement entropy, we should analytically continue this object to real n. What is the analytic continuation of this object to real n? Just let's take the same formula and assume that n is real. Okay? So in this case, the analytic continuation is very easy, it's just the same formula. So I can write down what I was calling frame entropy of order n as 1 over n minus 1 log of trace of rho a to the n. If I substitute that into this formula, what I get is c over 6 n squared minus 1 divided by n minus 1, 1 over 1 minus n, logarithm of a divided u minus v, plus log of Cn divided 1 minus n. Then if I just simplify 1 over n with 1 plus minus n here, what I obtain, and I invert that, c over 6, 1 plus 1 over n, log of u minus v divided by a, plus, let me baptize this object c prime n. It's not the derivative. It will coincide with the derivative for n equals to 1, but let's just call this ratio here c n prime. Okay? This is a very simple analytic function of n, and the entanglement entropy SA is equal to the limit for n that equals to 1 of this SA n, and we obtain c over 3 log of the distance between the 2 points divided by a plus this c1 prime. Okay. This is the famous results of Holtz and Larsen-Wilczek of 94, derived here, I think, in an easier way. If you see the original paper, it will be much more complicated. Okay. And you see the universal part that depends on this, only on the central charge, that is the logarithm of the distance between the 2 points, while this additive constant that appears here, additive in the sense does not depend on the distance between the 2 points, is clearly non-universal because a change of A changes this constant. So it's a non-universal constant that we will see later on today that has some universal content inside, but not directly. Okay? Okay, this is quite a crucial point, so please, if you have some question now, I would please.
So if you take the central charge to 0, you're left with this constant, does it have any particular interpretation?
Central charge equal to 0 is a non-unitary conformal field theory. Yes. That you can show, you can check. It has some application for two-dimensional statistical mechanical system. but does not correspond to any one-dimensional, one-to-one-dimensional system that has a unitary method. So there is no ground state of any physical system that has central charge equal to 0.
When we went from having a complicated worldsheet to the simple target space and then instead replicated the phi's many times, I don't see how that kind of plays a role.
Yes, just to write this formula, it does not play any role. Here I wrote the expectation value of t that was written here before, and now it's been erased, there is still some trace of it. From the expectation value of t, then I use the fact that twist fields are in this relation just to show up the dependence on the conformal identities. That it's the easiest way to see, but I didn't need this. I just, for example, I put T in the stress energy tensor as the reaction of the system to a scale transformation. Okay? You know, if I make a scale transformation, I can say lambda L, that is the only dimensional parameter in our game, derivative of the free energy, that means log Z in dL, is nothing but the expectation value of the stress energy tensor. By integrating that expression, I would have got exactly the same result. With the only difference that you don't understand actually why you should multiply by n. And okay, you can argue because you know the answer, but this that I show here with the twist field, I think is the cleanest way of doing it. But you don't need to do this. Just by having in mind this would be enough. But probably many of you would have said, where to this equation? And okay, so I prefer just to go in the clean way. Do you have other question on this? Because now we will play with generalization of this formula, so I prefer the things are clarified at this stage.
Just assuming that Cn, the log of Cn goes to 0 for every 1. So what is the behavior of the Cn coefficients?
The reason why this is the case, thank you for the question, I forgot to say, is that it's a physical reason, and it's the trace of rho in any case is equal to 1. Okay, you say, but this is something that comes from the first hour. Where is in the conformal field theory? In conformal field theory is that actually Rn, for n that goes to 1, is just a complex plane. So this relation should be 1. Okay? You can imagine this. You have to turn around. It's a conical singularity, basically, this object, with the opening angle of 2 pi n. So it's a very large conical singularity. But when you take the limit n that goes to 1, you just get a conical singularity of opening angle of 2 pi. That means no conical singularity at all. So you just get a complex plane and you get that normalization should be 1. How it goes to 1 in any case depends and gives this additive constant. Thank you, I forgot to tell this, I wanted to, so. Is there any other question? Now, I want just to stress once again that the crucial point in order to use all these simple things is just the fact that the theory is conformal invariant. And this is a very crucial point. Okay? And the fact that conformal invariance in 1 plus 1 dimension constrains the dynamic of the system a lot. Okay? In higher dimension, this is not the case, as you know better than me. And so one cannot play just like this. Conformal, there is, if I invent this crazy surface that is not Riemann because the passage between one and the other is not in a point but is in a strange shaped object, I cannot have a conformal transformation that maps one into the other because conformal group in higher dimension is finite dimensional. And I cannot map everything in everything, as instead I can do one dish. Okay, so, and there completely new methods should be invented But this identification of the twist field also allowed to make other calculations much easier. Okay? Once I understood that calculating trace of rho to the n is the same thing as calculating a two-point function of objects that behave like primary fields, I can just generalize this to a bunch of other situations. Like the first one would be to know what is the entanglement entropy at finite temperature. In this case, we have already seen instead of the plane, we have a cylinder of circumference beta. This is where we start from. Where we have a cut here between these 2 points U and V. Let's call this plane Z. And let's assume I want to know the entanglement entropy in this object, of this object. But since we say the trace of rho to the n is like the 2-point function of a primary field, and we know that under conformal transformation, primary field, let's write like this. Okay, where I'm saying that under a conformal transformation, a primary field transforms without any anomalous state like the stress energy tensor, but just basically each field take its scaling factor W prime Zj. This is just how much it dilates around the top. The derivative of the conformal transformation just represents how much the conformal transformation scaled the system locally, okay, to the scaling dimension of the fields. That's the reason why it's called scaling dimension, because it's how much the fields take, okay. So using this formula, we can calculate easily the entanglement entropy at finite temperature, just because we can take this cylinder and map into a complex plane okay, W. Let's call this, but okay, it's okay like this, into the complex plane W by means of the transformation Z equal beta divided by Q pi of W, or the inverse transformation is W equal Q pi Z divided by beta. Okay, you see that the periodicity of the cylinder is nothing but the periodicity of the exponential function in the along the imaginary axis. Okay, exponential function is periodic like sine and cosine, but on the imaginary axis. This periodicity is part into this. Okay, so what the logarithm does is to take cylinder and map to the complex plane. Okay, then we can just use, if we want to know this guy, we can just use this formula, and using the value on the complex plane of this object that we already have calculated, so we have no problem, okay, and see what happened. Let's do this, okay, we need clearly the derivative of V prime here. V prime is just Q pi over beta equal to Q pi Z divided by beta. That means Q pi over beta times W. Okay, so let's make the algebra quickly. Trace of rho a to the n, let's say, on the cylinder is equal to the absolute value of the derivative that we can take from here, q pi u, evaluated at the point z1 and z2, so e to the pi u divided by beta, e to the q pi v divided by beta, q pi over beta squared, 1 for each derivative, everything to the q delta n, that is c over 12 n minus 1 over n, times the 2-point function on the plane. And the 2-point function on the plane is this number Cn that we don't know, times e to the q pi u over beta minus e to the q pi v over beta divided by this lattice spacing A to the minus c over 6 n minus 1 over n. This is just simple algebra, just I plug in the conformal mapping to get this expression. Clearly from this formula, from this plot, I would have expected us to be depending just on the distance between u and v, and not by u and v separately. This is not yet manifest here, but just let's combine the things in such a way that it's manifest. You can see just that the power here is just half of the power here. So when I multiply this guy inside here, here I get u minus v, and here I get v minus u. Okay, so translation invariance is clear there.
Why it's minus now on the right side? Yes, confused a bit. So
Trace
of
rho a to the n, the formula that we just write was c over n. I wrote as a to the u minus v to the c over 6 n minus 1 over n. And okay, to not write a huge denominator and a small denominator, I put the minus, but you can write as like.
So here in double plane, there's also branch cut. There should be branch cut, right?
There is a branch cut if you want to work in a Rn. But all the trick of using twist field is that we can forget about the branch cut and just putting twist operator at the end of the branch cut. Okay, yes, I would have derived everything we using branch cut would be a bit more complicated. But it's the understanding of these twist fields made life easier. And okay, I would like to use this. What is it? So if I recombine these objects, what I get is c over n, Cn, sorry, beta divided by q pi, e to the pi u minus v divided by beta, minus e to the pi v minus u divided by beta, everything divided by a, minus c over 6, n minus 1 over n, where you see explicitly the translation invariance of the formula, and actually you can recognize also this combination as the hyperbolic sign. Okay, with this two here. So this object is nothing but Cn beta over 5 hyperbolic sign of u minus v okay, this is all absolute values, so write in the order that you prefer, divide by A. Let's put the A here. Okay, so this simple formula gives you the trace of rho to the n, that again depends on n only through this factor, so we can repeat exactly the same game as before for the real continuation. And if we do it, we obtain exactly the same function with a different argument of the logarithm. So the entanglement entropy is C over 3 logarithm of beta divided by A sinh by, let me call L the distance between U and B, right much, okay, plus C1 prime. Okay, and this is very nice and compact formula for the entanglement entropy. Yes?
So if I take beta to infinity now, to compare.
That's what I'm doing.
Yeah, so what I was just going to say, I mean, there's a beta in front, is that just going to get swallowed up by the normalization and overall normalization?
Okay, so now we take two units of this expression. The first one is that L, the distance, is much smaller than beta. That means beta that goes to infinity if you wish. In this case, you can replace the hyperbolic sinh by pi L over beta. Beta and beta go away. Pi and pi also go away. And you get C over 3 log L divided by A plus C1 prime. That's exactly the same results of before. Things are important. Things are consistent. And notice that the C1 prime is always the same number. It's non-universal, but it's the same guy going around all the time. So if I want to make a measurement that I'm not able to measure, I make a simulation that I create this object, and I get C1 prime at some finite, at zero temperature. If I repeat the simulation at finite temperature, I don't have another arbitrary constant. I have one non-universal constant fixed that once is fixed forever. Okay, so I don't have to repeat. But this is not the only limit where things get interesting, because I can take the opposite limit. L much larger than beta, it means very high temperature. In this case, the hyperbolic sign is just an exponential, so logarithm of exponential gives the argument. So I have C over 3 pi L divided by beta plus something over L to the 0, that is logarithm beta, etc., etc. That is not too much interesting. But you see the high temperature, the entanglement entropy, take a volume law, it scales like volume, so this is the volume law. But this is not only a volume, this is just the thermodynamic entropy. That for a conformal field theory is also called Stefan Boltzmann law. Usually you have studied, when you study black body radiation, the Stefan Boltzmann law in 3 dimensions, where you get L cubed for the entropy. Okay, but this and T cubed at the denominator. In 1 dimension, this becomes just L times B, L times T. This is the Stefan Boltzmann law in 1 dimension that was known before the equation of the entanglement entropy is not new. And actually, C in front here shows that C is just counting the number of degrees of freedom you have in the theory, like in the Stefan Boltzmann law. Okay, so this nice formula for the entanglement entropy, you see that in one simple formula you can interpolate between a pure quantum behavior, entanglement at t equal to 0, in a pure classical behavior, entropy at high finite temperature. In the middle, this object is well defined as an entropy of some reduced density matrix, okay? But it's not an entanglement measurement anymore. Why it's not an entanglement measurement? Because at finite temperature, the state is not in a pure state, but it's in a mixed state, and the entanglement entropy, as we constructed, give a measure of entanglement only in pure state. So in the middle, this object is well defined. If you want, you can calculate in your theory, you can calculate in your simulation, a bit more difficult to calculate numerically, experimentally, but it's a well-defined object, but it's not a measure of entanglement. Okay? It reduces to a measure of entanglement equal to 0, it reduces to a measure of thermodynamics at equal to infinity, and in the middle makes this nice form. Okay? Before the break that I would like to make soon, I want just to show a very simple variation of all this. And this entanglement entropy in a finite system. That means now I have a periodic system. Okay, so this is space now, and this is imaginary time. It's a cylinder like before, but it's oriented in the other way. And I want I have equal to 0, and I want to know the entanglement entropy of a finite region of length L, and the circumference of everything is big L. Okay, I could repeat the transformation as before. Instead of it e to the 2 pi L u z divided by beta, I should have e to 2 pi I z divided by beta. But the two things are just related by sort of big rotation. It's just saying beta of before into I L, and I get the same result. So if we make this mapping, what we get is that the entanglement entropy is C over 3 log L divided by pi A sine and not hyperbolic sine pi L divided by L. No way minus forgetting. Plus C1 prime, always the same C1 prime. No, too many log here. Yes, I was right before. So it's exactly the same formula as before, with sinh replaced by sine and L divided by beta. And this is the entanglement entropy of a finite system, a finite interval in a finite system. Okay? And this is the formula that is most used in all numerical work, because you always have finite system. But not only, this formula shows quite important properties. It's symmetric for L that goes in L minus L. That's something that should be, because now we are at 0 temperature, okay? Because we move from minus infinity to ground state. So it's symmetric for L in L minus L. That is the fact that SA is equal to SB. So that's, and all this is in a very simple formula. Notice that this formula instead, with the hyperbolic cosine, becoming something extensive, cannot have the symmetry SA equal SB. But in fact, it's not true. SA equal SB is true only because of Smith decomposition for a pure state and not for other state. Okay? Just for curiosity, you could wonder what happens if I have both finite size and finite temperature. In this case, you end up in a torus. Okay, so where, for example, this circle represents beta, the big one represents L, and we are interested in the entanglement of 2 points, or between 2 points. This corresponds to the calculation of a 2-point function on a torus. But since the torus has a non-trivial topology, as genus 1 and not genus 0 as before. I cannot map it to complex plane to use the results of before. And the calculation is much more complicated in this case. There exists some results for, actually there is only one result for the Dirac fermion by two different groups showing two different results to show that it's quite complicated calculation, and I think honestly it's far beyond the goal of these lectures. Okay, just to show you what are the complications that can happen in these cases. Okay, I think we should make a break and we'll be here in 10 minutes, no? Good sign. These are not cheap. I don't touch Miguel. Miguel is the best. Okay, so we can restart. Since the previous hour was a bit longer than the 3/4 hour, I will be a bit shorter in the second one, just to make some constant. And okay, let's see.
I have a question.
Already? Okay.
Before. When you do calculation in quantum field theory, you would expect some singularity in this quantity, no? I mean,
There was this A going around all time. Then clearly you cannot set to 0, just set the length.
Okay.
Like
no,
there
I
is
mean something to some additive factor, no? Something.
This is the formula that I have written a few
Yeah.
times now. You see that this is the UV
Also
cutoff.
some power law to be subtracted, no? I mean, if you consider the free energy, for example. You will have
Yeah, when you take the log, then this just becomes an active constant. That is this log A here. That exactly compensates between these two things, and it's what makes this object non-universal, because it depends on the UV cutoff. The fact that it grows like C over 3 log L is universal. The dependence on the cutoff is not universal.
That I understand. But for example, if you have, let's say, Casimir energy, you always have a constant, it could be also singular. No? I mean, and it's in the case of the Casimir energy, it's a difference of two energies that is the physical thing. No? Then you may have a cutoff dependent pieces, and this is not possible.
Trace of rho A to the n is the ratio of the partition function on the n-shaded Riemann surface divided z, what I call z1 to the n, and this is what is equal to tau nu, tau tilde and v. So what you are saying is that this object has a constant, this object has not the constant, but in the ratio, these two are the one that erase, as I said before, this volume law and etc. And what is left in trace of rho to the n already. Okay, so the partition function themselves have additive constant. In the ratio, these two guys just erase. Actually, the free energy is an additive constant. This is e to the minus f. So the additive constant in the free energy just erase in this ratio, and what is left is just the final things automatically. That's what I said at the end of this morning lecture. There are other questions on what I said in the previous hour. Okay, I think since we will play around the same arguments, I think if there are some unclear things we come out now, so let's just continue. And I want to show what happens in the case we consider a conformal field theory with a boundary. Okay, so boundary CFT. What is a boundary CFT? Is just, instead of having the infinite line as before, let's imagine to have a boundary that is the same in the time. So this is the space, and this is the imaginary time. At x equal to 0, just arbitrarily, we put a boundary that is the system is not on the other side, and we would like to know, for example, the entanglement entropy of a segment starting from the boundary of length L. Okay. In this theory. What does it mean in the replicated structure? Again, that when going around this point, we have to start n time to go back to the original sheet of the Riemann surface. And let's call this plane Z, and let's use that Z is tau plus Ix, so actually it's the rotated plane. And this object can be uniformized, this time into a disk. Okay, so the boundary here is set into a disk. Of unit radius, just for simplicity, it's the same. And this is the plane Z, this is the plane W. And what we have to do is just to make Z equal W minus IL divided W plus IL to the power 1 over n. This is just reproducing what we have done before. We have to, basically we are sending the interval here into an interval, into something starting from the boundary here. Okay? And the boundary is sent to the unit circle. You see from transformation, just put two random points of your choice into this formula, and you will see that this transformation makes the game. Now, if I repeat the game that I've done before, for calculating the expectation value of the stress energy tensor TW, it said actually in this n-sheeted Riemann surface that is different from the one before, so let me put a tilde just to say that it's another one, because it has this boundary here, boundary that is conformal invariant, whatever this implies. What you get if you use exactly the same formula before is delta n, where delta n is the same number as before. Delta n is equal to 3 over 24 n minus 1 over n. QL squared divided by W minus IL squared times W plus IL squared. And this object is equal to tau n, calculated in the point IL, Z, on the complex plane, divided by tau n IL on the complex plane. This time we introduce a single twist field, not two, because there is only one point between A and B. Okay? Again, looking at this formula, one can recognize the conformal identity of boundary conformal field theory that assume exactly the same form, so I don't rewrite, but you can imagine that I'm not cheating you with exactly the same formula. Okay, just with del, written usually with del replaced by some Z1. Okay, and so this ensures that the expectation value, the trace of rho A to the n, is equal to the expectation value of tau n in IL. Okay, is just equal to some constant C n tilde. That again, in principle, is different from the one of before. Divided by QL to the minus plus Q delta n. notice that as difference from before, there is a factor 2 here and not 4. This is because usually a boundary conformal field theory has half of the content of the other, as even you can see it's just a 1-point function, not a 2-point function. And this factor 2 that appears here, you can see just by thinking to the electrodynamic analogy that when you have a boundary, here imagine to have a charge plus, where you put charge plus, that in our case we put a field tau n in L. What you do, you just put a charge minus on the other side, and you put charge minus correspond to this tau and tilde in L, so that 1-point function on the plane corresponds to a 2-point function on the full space with the square root actually, because there is half of the things. So the distance will be 2L and not L, and the fact that there are the double of degrees of freedom correspond to a square root that change this 4 into 2. Just to give you an intuition how this formula comes out. Okay, that then in the future, if you ever work in these things, you will never remember the conformal one, and then you will just use image charges all the time. So better to know it from the beginning. Okay, so having understood this, okay, let's put also this lattice spacing here just to be consistent with before. And now we can take the entanglement entropy just by taking the limit n that goes to 1 to this formula, and that's before just because we have 4 instead of 2 instead of 4 here, we get c over 6 instead of c over 3, logarithm of 2l divided by a plus c1 tilde prime, where c1 tilde prime is the analogue c tilde n prime is log cn tilde divided 1 minus n, so the same construction just with the tilde. So this is the final formula for a boundary conformal field theory. And as you can see, there is a factor c over 6 instead of a factor c over 3. Okay? And this is actually can be interpreted as what is left by the area law in a conformal field theory. Before, between the interval a and b, we had 2 points. So the area was 2. Now the area is only 1. Okay, so we get half of the results of before. Let's say it's a residual of the area law. This is not constant, but say it's half of the results of before. And this is what is left. As in the previous case, it's interesting to take this formula and generalize to finite size and finite temperature. Let's make first the case of finite temperature. Yes?
What happens if the boundary doesn't, I mean the L doesn't go all the way to the boundary? You get a 2 and then...
If this object does not go all the way to the boundary, if I have a boundary here and there will be an entanglement between an interval here, as you can see, by images, you have a 4-point function in the plane. Then, okay, I will maybe briefly discuss just to tell that calculating 4-point function is much more difficult. And okay, it's a full, much more difficult. This clearly, in the case when, if you call this R and this L, in the case where L is finite and R goes to infinity, I go back to C over 3 log L. Okay? But in the middle, it's a very complicated formula that depends on the Riemann theta function and all the complication of 4-point function. That I will briefly mention, but without showing calculation, because it's really will take more than the 10 hours that I have, and I don't think you will learn a lot more than just by reading the table. Okay, it's just technicality and not physics. Instead, in the finite temperature calculation, there is a nice parts of physics, because let us understand something else about these constants here that I want to discuss now. So let's take the same game and go at finite temperature. So at finite temperature, I have a cylinder of circumference beta. Okay, so this is the time, this is the x, but we have a boundary, so let's assume here there is a boundary. So it's actually alpha cylinder, not a full cylinder. And we want to know the entanglement of a slit that starts from the boundary, because it's the only one we can do easily, up to some point, if, again, z is equal to tau plus I x, this point here is simply IL. And again, if we use the exponential mapping, same as before, it just rotated because I draw the cylinder in the opposite way. So, if this is the plane Z, I already wrote. If I use the transformation W equal e to the I cube pi Z divided by beta, I end up in a circle. Okay, where this is the boundary that was down here. If this is the center, the slit arrive here at some distance rho from the origin. Okay, but the slit is the other part of the rho. So what I have to calculate is the one-point function in this geometry. Tau n, let's say, of rho. That's just the c tilde n divided by rho squared minus 1 to the 2 delta n. Rho squared minus 1 is exactly this object here. Okay, now it's mainly algebra, and I don't want to repeat all the algebra. I invite you to make the calculation. Just I gave you the mapping. You have to plug the conformal transformation. There is only one point, so there is only one derivative to be put in the mapping. If you make the calculation correctly, to save some time, you arrive in the end to the result for the entanglement entropy, that is C over 6 log beta divided by pi a sinh q pi L over beta plus C1 tilde prime. Okay, this is very similar to the formula of before, just that this tube enter maybe in an unpredictable place. Maybe someone that say it will go here, not it goes there. This is the only non-tricky part. The rest would be just guessed by any of us, I imagine. But it's the same formula before. There was a tube, that, like the one that was appearing here. And when you write in terms of hyperbolic sign, to get the right limit, you don't know where to put the tube, if inside the hyperbolic sign or outside. Proper calculation shows it goes inside. Okay, I don't have an intuitive argument to. Actually, I have an intuitive argument to suggest this that I will show now in a second. That's the following. The tip of this formula, I take the same two limits of before, okay, that are L much larger than beta, L much smaller than beta, that means the very high, very small temperature. I got back to this result here, C over 6 log QL divided by A plus C1 prime, simply because I can replace the sinh with this argument and get the same result. But now, if I go to very high temperature, L much larger than beta, I can, Sinh is basically the exponential of 2 pi L over beta. The 2 exactly compensates the C over 6 that is here, and in fact I get C over 3 pi L over beta plus C1 beta prime. And these results, the extensive part is exactly the same as before. It's extensive, depends on the length of this interval, cannot depend on the fact that I put a boundary here. So this would have been a priori reason to understand that the 2 should go inside the sign, metabolic sign, not outside. If I would have get the opposite result, it would have been that I was wrong, because I should reproduce an extensive result that does not depend on the boundary. What can depend on the boundary that is localized in space is only an additive constant, that is this C1 theta prime here. But what is now this constant? It's not the same constant as before, but should be related to the constant of before, because if I have a full system, everything should be similar, just with a difference due to the boundary. Okay? In fact, this formula for the entropy at high temperature, the analogous of Stefan Boltzmann law for system with boundary, was already written in a paper by Affleck at very high temperature. The entropy for the free energy that is the same was already written in the 88 in a paper by Affleck and Ludwig, where they say that the difference between these 2 objects, the one that appear for free without boundary condition and the one with the boundary, are related indeed, and they are C tilde 1 prime minus C1 prime half equal log G. And this object is the boundary entropy, was termed by these people. Of Affleck. That is the non-integer degeneration of the boundary state. Okay? So, at very high temperature, these 2 constants are related in this way, by going back to Affleck and Ludwig. This means that at any temperature, including 0 temperature, where there is no dynamics at all, these 2 constants are always the same because they are additive, we say they are not universal, but they don't change due to calculation. But the 2 constants that appear even at 0 temperature should be just given the difference in this form, this factor 2, counts the fact that there are 2 boundaries exactly in the 2 points between the 2 as before. It's just the logarithmic boundary entropy of Affleck and Ludwig. This is an object of conformal field theory that is calculable. Okay? For example, just to give the case that is very easy, is the Ising model, where you can have fixed and free boundary condition. Fixed boundary condition means that all the spins are up or down in some direction. If all the spins are fixed, there is no entropy in the states. They are fixed states. So G is 1. There is only one state that makes this. Okay? And log G is 0. Sorry, it's vice versa. If it's fixed, there are 2 states that make this, the one up and the one down. That makes, so it's that difference exactly log Q. And this can be checked, and that's been checked in numerical simulation for this case, while making proper calculation in this case is basically impossible, and no one was doing it before. This became possible just with the entanglement entropy at 0 temperature. Okay? And in the other case, when I have free boundary condition, meaning that spins point wherever they want, this is only one, it's the permanent state that has no degeneration, and so log G is equal to 0, and these 2 constants are just related like this. Okay? And then for all the conformal field theory, there are a set of boundary states, there are a set of boundary entropy that can be calculated, and okay. That it must be said also that log G, this G, okay, log G, is the analogous of the central charge for the boundary. The central charge, you are aware probably of the C theorem of Zamolodchikov. This under normalization group, the central charge of a conformal field theory cannot increase, always decreases. Okay? So if I apply some perturbation that is relevant, I go somewhere else, and central charge passes from one value to a value that is smaller than the one of before. And this was proved by Zamolodchikov in the 88. There was a conjecture, actually due to, I think two authors can look at themselves, let's say that in the boundary conformal field theory, the role of the central charge is played by the log G. It means I have all my conformal field theory, okay? I have flow over G that brings from here to here, and if the central charge of this theory should be smaller than this. But for fixed bulk theory, I have several boundary theories. So it's like if inside this, there are indeed 3 points. When I fix this, and I make the flow between the boundary, the quantity that decreases was proposed by Angelantonj to be this log G. Okay? This conjecture was proved just in 2005 by Friedan. Okay, there was something very relatively recent. And okay, again, the fact that the central charge appears both that for the leading term the central charge appears in the entanglement entropy, and for the subleading term it appears the boundary entropy, have proposed big speculation on the field, etc. If the C theorem, irreversibility of the RG flow is somehow connected with some increasing of entropy, entanglement, etc., etc. There are some papers on this. There is an F theorem proved for the leading term, not for the boundary. Nothing is known yet. But so there are several connections with what we have said. Okay. Perfect. Are there questions on this? Like a critical point.
You don't fix, you say L. So it's only for the critical point, you have base transition, so it's not wrong.
Yeah, it's for the Ising model.
But here you don't fix L, yes? What's L, physical meaning of L, what you have in SA, for instance? In entropy, what's the L meaning of L, physical meaning of L for Ising model?
It's the one we started from. Take an Ising chain made of, okay, in total I have big L spins. I consider just a small part of them L. I construct the reduced numerics of this object. I construct the reduced numerics of all the L spins. It's a 2 to the L times 2 to the L matrix. Rho A of distance L is a 2 to the L times 2 to the L matrix. It's a huge object that can be constructed analytically. In the case of the Ising model, in other cases, the more complicated chain can be studied numerical. And, okay, maybe it's not here the right place to explain why, but calculating the entanglement entropy in a numerical simulation is the easiest thing that you can do. Okay, basically, when the entanglement entropy started becoming popular, people just added a line on the code that they already had because they were already calculating the entanglement entropy, just they were not asking the computer to give the number. But it's just a natural byproduct of one algorithm based on density matrix, normalization group, metric product states, and these kind of things. So it's not at all something complicated. It's the easiest thing that you can do, even if by definition looks so crazy, but they required to explain how the numerical simulations are done. Okay? But in fact, nowadays, if you want to know the central charge of some model, usually you just calculate the entanglement entropy. And this is the most effective, the quicker and more precise way of calculating the central charge of a model that you don't know the central charge. Okay, so this we can discuss later why. It's clearly you need to know how this algorithm works. But apart from that, it's very easy goal. Okay, are there other questions? Okay, if there are no other questions, and by the way, this is exactly the way how this log G has been measured, especially in a numerical simulation. You take the IC model, you make the simulation with free and fixed boundary conditions, you subtract the logarithmic part, you make the difference between these two objects that are not universal and you don't have any prediction for them, but their difference is just given to this log G, and you get, in the case of fixed boundary condition, log Q very nicely. I want to spend also 2 minutes to say what happened in finite size. Finite size with boundaries. In this case, always drawing in this way. So this is the full dimension of the system big L, like the spin of before. This is the Z plane equal to tau I x. I consider a small interval starting from one of the boundaries of length L, I, L. Okay, and I want to know the entanglement entropy of this object with the rest of the system. Again, I can map this into the upper half plane, where half of this is on one side, when this is on half of the half plane, this is on the other half. The transformation that makes this is just W Z equals L over pi log W. Okay, notice there is only one pi and not 2 pi in such a way that the part with the imaginary real part equal to 0 goes on the positive real axis, and the part with the I pi plus something goes in the real negative axis. So if here is minus 0, this is this lower edge of the strip, and this is the upper edge of the strip. Okay? So this is the conformal transformation. The point I had was just something here. You follow the transformation, you make your algebra as before, I don't write, and what you get in the end is that the entanglement entropy is again C over 6 log QL divided by pi sine of pi L divided by L. Notice that this time the 2 went outside of the sign, so it's quite different from before that there was no ambiguity. In fact, I cannot just take this object and map into the other by a weak transformation. I should repeat the calculation. It's very similar because it's always a log that is around, but it's different, and where the 2 appears is different. And also this could have been easily guessed because we always need the symmetry L that goes in L minus L. That means SA equal to SB. If this is A, this is B. Okay, and only the sign has this property, not sine 2 pi. Okay. Okay, probably in the remaining 5-10 minutes, instead of starting something new, that is where I prefer to leave for next Friday, that is what happened in massive quantum field theory in one dimension, etc. I want just to sketch what happened in more complicated situations. Okay, clearly I will not derive anything because it's too complicated, but it's good to know, and in particular for people that are working on a subject or in similar subject. In one of the more complicated situations that is very interesting is to have always a one-dimensional system, and instead of having one interval, we have two intervals. U1, V1, U2, V2. That means we put a tau n here, tau n tilde here, tau n tilde. And what I want to know is the entanglement. These objects correspond to the entanglement entity of this Q interval with respect to the rest of the system. It's not the entanglement of one interval with the other one. But the entanglement of the Q interval with respect to the rest. That means A is done of this Q disjoint part, and B is all the rest of the system. It's always a B partition. Okay? The same construction of before for trace of rho A to the n is valid. Means that this is equal to tau n u1, tau tilde n u2, v1, tau n u2, tau tilde n v2 on the complex plane because I put the tau. But now I should calculate a 4-point function. And calculating a 4-point function is extremely difficult thing in conformal theory. Okay? But still, we can give some general result based only on global conformal invariance. That is, that this object should be of the form Cn squared. 1 minus. I write before the formula and then I will discuss. Okay, so depends on these 4 points in this not so complicated matter. So this is a piece fixed by conformal invariance. This is a function that is the difficult part of the game. How we can understand this piece that is fixed by conformal invariance? Okay, imagine to have 4 points in the plane. U1, V1, U2, V2. And as I was saying before, the U have all charge positive and the V has charge negative. Okay. This is just the Coulomb potential that you get with some strange power, okay, that are erased by the fact that is a conformal field theory with these charges. Exactly like before, and you see that charges of the same kind are the denominator, are the numerator, so they repel each other, while charges with the opposite charge, the distance between the two, are all in the denominator, and they attract each other. Okay? So, just by Coulomb-Gas analogy, you get all the prefactors that appear here. Okay? And this can be worked out easily, but honestly, I even don't remember how to do it. I just remember the Coulomb-Gas analogy, and this is what you should do also after, not just go to the book and check it, but saying for any 4-point function this is true, okay? Depending on what are the fields, obviously, they are properly done. And this x that appear here, that is the complicated part of the game, is the so-called 4-point ratio. That is the only invariant that you can construct with 4 points in a CFT. Okay? And that's the expression U1 minus V1, U2 minus V2, divided by u1 minus u2, v1 minus v2. And this is the only independent dimensionless quantity that you can construct with 4-point with a conformal field theory. And the way to understand this, also there is an easy way, is again, you have 4 points wherever you want in the plane, not even to be in a line, and with a conformal mapping, you can map 1 point in 0, 1 in 1, and 1 into infinity. And there is only one guy left, and this is what it goes to x. In fact, the conformal transformation that makes this mapping is a linear function, and you see that the point that you don't map either to 0, 1, and infinity goes into this number. Okay?
Excuse me.
Yes?
In this case of two intervals, how is the uniformization map between the two?
There is no uniformization map. And, okay, so, you want, first of all, this is what it is from global conformal files. It's clear? Okay, so, I have to calculate this 4-point function. I don't know in general how to get it, but the general form is fixed by global conformal invariance. Notice that here there is this constant Cn squared that is exactly given by the fact that if I take these two intervals and send very far apart, I have just twice the entanglement entropy of one interval. Okay, that is this u1 minus v1, u2 minus v2 that appear here, and this ratio was just to 1 when I send the two intervals apart. So the Cn squared again is the only was the only non-universal part, but it's fixed by the calculation of before. There is no new non-universal object in this calculation. Okay? Understood this?
So,
Let's make a draw of this Riemann surface.
so could I ask one stupid question? Why we couldn't have tau m, for instance, on the right side?
Because I have an n sheet. I want to calculate trace of rho. My goal is to calculate the entanglement entropy that is limit n equals to 1 of trace of rho a to the n. Okay, and I want to make. Yes, but I want to take the limit n that goes to 1. I take the same object. What I'm constructing is the following guy. I have one plane, two plane. Please just let me make two because it becomes too much complicated. Okay, so I have to join this like this, and this like this. It's not very clear. Okay? You see, both intervals should be joined in this cyclic fashion, but in the middle nothing happens. Like this, it's very little clear. Let me redraw. Okay, and instead of this strange line, let me put just a band here. A band here. Okay? And you see that in this drawing, there are these two planes with these two cuts in the middle, and here there is an O. Okay? In fact, you can slightly take this object, deform slowly, and you arrive to a torus. So this object can be mapped not to the plane, but to the torus. So the genus of this guy is 1 for two interval. Actually, for two interval and two sheets. If you have more sheets, like cube, you get two O's, not one O. So you get a genus 2 Riemann surface, and in general, the genus of Rn with two intervals is n minus 1. And this is what makes the calculation complicated. We cannot map this object to the complex plane because of Riemann theorem. Okay? You can just map surfaces that have the same genus. Okay? So the genus is n minus 1. It's not mappable to the complex plane, and actually for each n is mappable to a surface with a different genus, different topology. The calculation is much, much more complicated, and people that are interested just in looking how to do it can check in these two papers by myself, John Cardi, and Eric Tonni. J-Stat P11001 of 2009 and J-Stat 01/021/2011. It's 30-something page each, so it's quite and all of calculation. Just to show how to do this, it's extremely technical and not very much to learn about a bit of topology from the pedagogical point of view, but from the practical point of view there is a lot. Okay, and okay, so you can imagine why calculating this function then is very complicated. If for the people that know what the functions that enter into the game are, I can write the result for a compactified string boson. That is equal to theta of beta gamma, theta of gamma divided by theta of gamma squared, where theta is the Riemann-Siegel theta function defined on the period matrix gamma. Okay, and calculating this period matrix is the difficult object, because basically one should understand how these surfaces are mapped to uniform tori, or bitori, tritori, as you want. So I didn't don't write the expression of gamma here because we take all the blackboard. And just eta is the square of the compactification radius of the boson, just to see. And really, this is for the experts, not for the students. I still don't understand why for eta that goes to 1, this Fn is equal to 1. It's the supersymmetric point. Everyone knows this, that it's the supersymmetric point, but for the supersymmetric point, this scaling function is exactly equal to 1, and I don't have an explanation for this being in a field where supersymmetry, in a place where supersymmetry is much more known than what I know. Maybe it's the right place to say that this object is equal to 1, and I don't, for eta it goes to 1, and I don't see the reason. So if you can help on this, it's fine, and I will stop here. Thank you. The compactification radius. It's proportional to the square of the compactification radius. And for r equal 1 is the Western-Witten model that has is supersymmetric, and it's the only point supersymmetric for a compactified boson. And why it's 1, it's the Neumann